Hello everybody, I'm Sofia Ventura. I'm a PhD student at University of Siena and NFN Pisa in Italy. Today I'm going to present the very high energy detection of the extreme Blazar 1RXS J0812 with the MAGIC telescopes. The outline of this presentation are a brief description of the MAGIC telescopes, a bit of physics about blazars, extreme blazars, how to select these sources, our candidate, the multi-wavelength coverage, and the future of 1RXS 0812. MAGIC is a system of two telescopes operating in stereoscopic mode to detect very high energy gamma rays each our atmosphere, using the imaging atmospheric Cherenkov technique. Among the sources that a Cherenkov telescope can detect, there are blazars. A blazar is a radio-loud galaxy, a subclass of active galactic nuclei characterized by a relativistic jet points towards our line of sight. They are the powerful accelerators in the universe and the most variable sources in the gamma sky, characterized by non-thermal emission from radio to gamma rays. Blazars are divided into classes: the flat-spectrum radio quasars, characterized by broad emission lines in the optical spectrum, and BLAC objects, without broad emission lines in the optical spectrum. The synchrotron self-Compton model is able to reproduce the broadband spectral energy distribution and emission from these sources. The SED are characterized by two separate components. The first one is the synchrotron peak, and the second one, the inverse Compton peak. In flat-spectrum radio quasars, the first peak, the synchrotron peak, is in the infrared range. Instead, in BLAC objects, we have three different classes: the low-frequency peaked object, the intermediate, and HBL, the high-frequency peaked object, with the first component in the UV and soft X-rays. Extreme blazars are the extreme flavor of HBL. So, in this case, the first component, the synchrotron peak, is beyond the soft X-rays, and the second component, the inverse Compton peak, exceeds hundreds of GeVs, and in some cases can reach TeV energies. In general, they are extreme faint sources. Why is it important to observe extreme blazars? Because EHBL are ideal laboratories for testing physical theories, and depending on the hardness of their very high energy gamma ray spectrum, we can distinguish between two classes and two scenarios. In the first one, we can study particle acceleration processes and emission mechanisms within the source. And in this case, the intrinsic spectrum has a spectral index at very high energies greater than 2. So in this energy range, this source has a soft spectrum. We have the first flavor of extreme blazars, the so-called extreme synchrotron sources. The second flavor, the so-called extreme TeV sources, are important in the rising cosmology with gamma rays. And in particular, we can study propagation effects in the universe, such as to constrain the intensity of the extragalactic background light, the strength of the intergalactic magnetic field, and they are fundamental in multi-messenger studies too. In this case, the intrinsic spectrum has a spectral index at very high energies, less than 2. So in this energy range, these sources have a hard spectrum. In the first EHBL catalog of the MAGIC collaboration, 3 models are used to model the broadband spectral energy distribution. And in the first model, we have a time-dependent description of the emission in an expanding jet. In this case, this model is a one-zone model, since the emission arises only from one region within the jet. In the second model, the so-called spin layer model, we have two different regions within the jet in which the emission arises. In this case, we have two-zone model. The third model is a leptodronic model, in which the proton synchrotron emission and radiation causing the very high energy gamma rays. This is the link with the neutrino astronomy and to test if AGNs are the accelerators of ultra-high energy cosmic rays. To select these sources, the multi-wavelength coverage is fundamental in hunting EHBL. In the first EHBL catalog of the MAGIC collaboration, an approach used consists in 4 criteria. In the first one, we have the observation in the X-rays, and in particular with the instrument SWIFT. They are important because the first peak in the SED is in the soft X-rays. Moreover, the spectrum is hard in this energy range with a spectral index less than 2. Moreover, the synchrotron tail can reach hard X-rays, and so we can have a chance to observe this source with new stars, for instance. The second criterion consists in the observation in the high energy band, and so the sources listed in the Fermi-left catalogs. The third one is the estimation of the ratio between the flux in X-rays and in radio, and it has to be greater than 1. The last point is the measurement of the redshift. In this case, it has to be moderate and so less than 0.2, because in that case, the absorption due to the extragalactic background light is moderate, and so we can have a chance to observe these sources with Cherenkov telescopes. On the bottom right, you can see an example of the spectral energy distribution of the prototype EHBL sources, the 1ES0229. In this case, all the 4 criteria are respected, and here you can see the 3 models that I presented in the previous slide. And we have a third component, an extra component in the spectral energy distribution at high frequency. In this case, the third model provides a third bump in the SED, and it is the expected neutrino flux. Our candidate is an extreme blazar. It is a promising source for observing with Cherenkov telescopes because its radio, X-ray, and high-energy fluxes are compatible with the EHBL prototype 1ES0229. The multi-wavelength SED shows that the synchrotron peak is around 4 keV, so in the soft X-rays. And we have the measurement of the redshift. And also, in this case, the 4 criterion is respected. MAGIC observed this source during 2 observing campaigns, collecting around 50 hours of data. Here on the left side, you can see the detection plot, and 5 sigma is reached. On the right side, you can see the spectral energy distribution obtained with that observation, and on the bottom, you can see the estimation of the parameters of the power law fitting the data. Please note that the spectral index is greater than 2, so in the very high energy range, this source has a soft spectrum. Regarding the multi-wavelength coverage, there is an ongoing X-ray monitoring, and in particular on the right side you can see the broadband SED with, in gray, the archival data, the UV data. They are fundamental for studying the host galaxy, the X30 data, the Fermilab data, and MAGIC data. On the left side, you can see the Fermilab SED, and on the bottom, you can see the estimation of the parameters of the spectrum obtained with the Fermilab analysis. What about the future of this source? Since, as we've seen previously, since the very high energy gamma ray spectrum is soft at very high energies, this source belongs to the first flavor of extremer blazars, the synchrotron peak sources. With this source, we can study emission mechanism and particle acceleration processes, and test several models, such as lepto hadronic models and one-zone models or two-zone models. This source will be listed in the second EHBL catalog of the MAGIC collaboration, and 1RXS 0812 will increase the population of the TV catalog. Thank you for your attention.